Excellent. So welcome everyone. Thanks for joining the October SimPEG seminar. As folks know, this is something we've started this year. And so this is the, I think, fourth SimPEG seminar that we have been giving. And so it's something we do each month. Next month, I believe, will be Craig Miller. And then we're looking for folks after that. And so if you are interested in giving a talk or there's somebody you know that you would like to hear from, please feel free to get in touch and we can line up some talks going into the new year. And so today I have the pleasure of introducing Xinyan. So Xinyan Li is a PhD student. She's doing her PhD degree in geophysics in the Department of Earth and Atmospheric Sciences at the University of Houston. She's working with Jiajia Sun. She received her BSc degree in geophysics in 2017 from the University of Houston. And her research interests focus on maximizing the value of geophysical data through 3D mixed LP norm inversions and geologic differentiation. She's currently working on joint inversion and recoverability analysis using multiple potential field data primarily applied to mineral prospectivity in the Quest project area in British Columbia. And so with that, I will hand it over to Xinyan. Thanks for joining us.
Yeah, thank you. Thank you for having me in the SimPEG seminar. So I will start sharing my PowerPoint. Can you all see my slides on your side?
Yes, that looks good.
Oh, thank you. Okay. So now I'll begin my presentation. So hello, everyone. My name is Xinyan. I am currently a PhD student at University of Houston, and Dr. Jiajia Sun is my advisor. So in this following presentation, I'll present our work where our research objective is to investigate the recoverability of physical property relationships from different geophysical inversions by using multiple potential field datasets, such as gravity and magnetic data. So the outline of the following presentation is as follows. I will firstly go over the general workflow of implementing multiple potential field data, including the research questions, which then triggers our research motivations here. And then I'll briefly go over the inversion methodology and the design of the experiment. The core part will be the analysis of the recoverability. And lastly, we'll end up with conclusions and recommendations from our work, as well as a preview for our future work. So as we know, collecting and using multiple potential field datasets to image the subsurface of the geology has been popular in recent resource explorations. For example, in the regional Quest survey at British Columbia of Canada, there are multiple data types, including the gravity and magnetic data. After getting the data sets, how to effectively integrate them and extract as much useful information from them is still an active area of study. And the UBC group has also contributed a lot of work on integrating multiple potential field data sets. So the general workflow of geophysical inversions and interpretations contains two steps. The first step is using multiple geophysical data sets, such as gravity gradient data and the magnetic data to do geophysical inversions. And then the second step is using the scatter plot based on the recovered values, along with any available geologic information together to do classification, which is a process of classifying the inverted values into different groups. And then we can visualize those classified units in 3D spatial domains to produce the final product, which is named as a 3D quasi-geology model, which can be used as a representation of the subsurface geology and used for future decision makings. And the process of classification based on inverted values will be referred as geology differentiation from now on, and it has shown promising results in many literatures. So in this general workflow, the implicit assumption is that the recovered physical property relationships are reliable representation of the subsurface geologic anomalies. So just to make sure that we are on the same page, let's start with defining the physical property relationships by using an example scatter plot shown here. In this scatter plot, the x-axis is for density contrast value, and the y-axis is for the magnetic susceptibility values. And there are three distinct linear trends that are well separated, corresponding to 3 geologic anomalies. This blue linear trend for geologic anomaly 1 has a negative density and positive susceptibility values, and with a negative correlation. This yellow linear trend for anomaly 2 is above the red linear trend for anomaly 3, and both of the 2 anomalies have positive density and susceptibility values with positive correlations. Since our objective is to investigate the recoverability of physical property relationships, so what do we mean by recoverability? We can demonstrate it through some examples. Here is a true scatter plot with 3 distinct linear trends. After performing the smooth inversion, in its scatter plot, there are only 2 scattering features are recovered. And if we compare these scattering features, which are not exactly linear trends, if we compare it with a true scatter plot above, we can notice that it has lost 1 linear trend. Therefore, we can call this scatter plot a poor recoverability of the physical property relationships. In contrast, after performing the sparse inversion, we can say that in its scatter plot, there are 3 distinct linear trends are recovered, and they are at similar relative positioning with the same size and correlations as that of in the true scatter plot. Therefore, we can call this a good recoverability of the physical property relationships. As we have already mentioned, the assumption of the geology differentiation is that the recovered physical property relationships are reliable representation of the geology. For example, this is a scatter plot showed earlier from field data joint inversion. But the question is, are the recovered physical property relationships displayed in this scatter plot reliable? Therefore, in order to answer this question, our first motivation is to use different geologic scenarios with anomalies embedded at different depths and assigned with different physical property values to develop a better understanding of the recoverability. Moreover, when it comes to regularizations, it is well known that the conventional smoothness-based L2 norm inversion would underestimate the physical property values and produce smooth models. So how would it affect the recoverability is also underexplored. Well, on the other hand, the sparse norm inversion has proved to be able to recover anomalies with more compact boundaries and elevated values. So would the sparse norm inversion help to improve the recoverability? Therefore, our second motivation is to understand how smoothness and sparse regularizations will affect the recoverability. So to do that, for each geologic scenario, we have performed 4 different geophysical inversions, which are the separate and joint smooth inversions in L2 norm and the separate and joint sparse inversions in mixed L1-2 norm. And for each inversion result, we have also performed the geology differentiation and visualize them in 3D spatial domains. So in the separate inversion methodology, the cost function phi m is the sum of the data misfit term with a weighted model regularization term. And in the conventional L2 norm regularization, all the 4 components in the model regularization terms are in the L2 norm. While in the mixed sparse L1-2 norm regularization method, the L1 norm is imposed to the smallness component, and L2 norm is applied to the 3 smoothness components. So in the joint inversion, we have implemented the cross-grading coupling constraint method proposed by Gladu and Meiju. So the objective function for the joint inversion can be generalized as the summation of the cost function for each data type, along with the weighted coupling constraint. So in order to investigate the recoverability of the physical property relationships, we have designed 6 geologic scenarios with anomalies at different depths and assigned with different physical property magnitudes. And in each geologic scenario, the geologic model contains 3 realistic geologic anomalies. So the North Decor unit here in red color is constructed based on the previous study in the Decor area located in the Northeast Iowa. And the 2 southern ovoid bodies labeled here as a Southwest ovoid in blue color and Southeast ovoid in yellow color. They are constructed based on the sulfide ore body shapes in Voisey's Bay. So I will firstly introduce how scenario 1 is constructed. So here displayed the synthetic density contrast model per sections. This is a depth slice at 200 meters. And we also have two vertical slices at 800 meters in the south and 250 meters in the north. The y-axis here is the depth. The x-axis here is the easting. And similarly, we have the synthetic magnetic susceptibility models. Displayed here are the corresponding three slices. In our model, we have three anomalous bodies. This one in the ring shapes is designed based on the anomaly recovered from the decor area. So we'll refer it as the North Decor or ND unit. And it has a maximum density of 0.3 gram per cc and a maximum susceptibility value of 0.05 with a depth to the top of it of 125 meters. Notice that the values of the anomaly is not uniform. It is smoothly varying. That's why in the scatter plot, the density contrast versus susceptibility value relationships shows up as a linear trend for the North Decor unit. Also, we have two other anomalies in the south. The southwest ovoid, which displayed here as a blue linear trend, has a negative density contrast and a positive susceptibility with a negative correlations. And the southeast ovoid body shows up here as a yellow linear trend, has a positive density contrast and susceptibility values, and it is higher above the red linear trend with positive correlations as well. So besides the scenario one that we have just introduced, there are totally 6 scenarios, and they can be characterized into 3 different groups. So in the first group, the first 4 scenarios, they contain anomalies with the same physical property values, so that the scatter plot for each of the 4 scenarios is exactly the same. And the only changing condition is the depth of the bureau bodies. In the second group, we can compare between scenario 2 and scenario 5, where the anomalies in both scenarios are placed at same spatial locations, and the only changing condition is the physical property magnitudes of the anomalies. And in the third group, we have a special scenario 6, where it contains 2 anomalies at different spatial locations, but they share the same physical property relationships. So here are more details in the first group that differ in different depths. This is a scenario 1 that we have just introduced, which are shown here again. And for scenario 2, it shares the same density and susceptibility model parameters with scenario 1, and it has a deeper North Decor unit. And similarly for scenario 3, it shares the same physical property relationships with the previous 2 scenarios, and it has deeper ovoid units. And lastly, we have scenario 4, which also shows the same model parameters with the previous 3 scenarios, and it has deeper units for all 3 anomalous bodies. And they are among the 3 unit bodies, they are at relatively similar positioning with that in scenario 1. Also, in the second group, in order to investigate the effect of the physical property magnitudes, we can compare between scenario 2 and scenario 5. Here displays the scenario 2 that we have just introduced. In comparison with scenario 2, scenario 5 anomalies are at the same depths, but its North Decor unit has a higher susceptibility values. Therefore, in its scatter plot, the red linear trend for the North Decor unit is higher above the yellow linear trend for the southeast ovoid. And in the last scenario 6, there are 3 anomalous bodies, and 2 of them, the North Decor and southeast ovoid, they share the same physical property relationships. As shown in its scatter plot, the red linear trend for the North Decor unit is overlapping with the yellow linear trend for the southeast ovoid. So in each geologic scenario, based on the synthetic density and susceptibility models that we have designed, we simulated the gravity and magnetic data. Each data set contains more than 2,000 measurements. So the first row here shows the observed gravity data maps for each of the 6 scenarios. And the second row here shows the observed magnetic data for each of the scenarios. So firstly, To investigate the effect of burrowed depths of the source body, we will compare among scenario 1, 2, 3, and 4, where they share the same physical property relationships, but with different depths. So specifically in scenario 1, we have performed 4 different geophysical inversions. And here shows the L2 norm separately inverted density and susceptibility model cross-sections at 200 meters depths. When its inverted values are visualized in the scatter plot, which shows here, there are 2 prominent wing-shaped scattering features that are classified in blue color and yellow color. Each color here is defined by its distinct ranges of density and susceptibility, and each color represents one unique geologic unit. And when these 2 classified units are mapped into 3D spatial domain, we can visualize them through 3 cross-sections here, the depth cross-section at 200 meters and the 2 vertical cross-sections. Notice that the north decor unit is misclassified as the same unit with the southeast ovoid, since their scatters are mixed up and inseparable based on this scatter plot. And also, moreover, we can say that the volumes of the inverted anomalies are overestimated, which is understandable because their values are underestimated. In comparison, the L2 norm joint inversion has recovered sharper linear features, and it has recovered all the 3 anomalous bodies. Then from sparse norm separate inversions, the inverted values are elevated, and the volumes of the recovered bodies are shrinked, and also the scattering features in the scatter plot are better defined and separated. And lastly, from the sparse norm joint inversion, the recovered linear trends are much sharper and better delineated, especially for the north decor unit, because it is better imaged in both shapes and volumes. So based on those observations, we have observed that the sparse norm inversions results will make the geology differentiation easier, and the sparse norm joint inversion produce the best recoverability of the physical property relationships. Moreover, in scenario 2, the north decor unit is brought to deeper depths, so it is expected to be much less recoverable. And from both separate inversions in L2 norm and mixed L12 norm, there are only 2 wing-shaped scattering features are recovered, and the scatters for the deeper north decor unit is mixed up and inseparable based on the results. Therefore, in the geology differentiation, the north decor unit is misclassified as the same unit with the southeast ovoid. Well, in contrast, joint inversion have recovered much better linear features, but the linear trend for the deeper north decor unit is much shorter. And in the sparse norm joint inversion, the linear trends become much longer and more visible, and therefore easier to be differentiated. Therefore, it implies that the sparse norm joint inversion helps to recover the linear trend even for the deeper units. Moreover, in scenario 3, all the 2 south ovoid bodies are brought to deeper depths, which also create big challenges in their recoverability. So from L2 norm, both separate and joint inversions, these 2 deeper ovoid units correlation trends are smaller. Therefore, they are more difficult to be differentiated. However, with the help of the sparse norm inversion, these 2 scattering features become larger and more visible. And with the help of the sparse norm joint inversion, we get a much better recoverability because the linear trends are better defined and separated. And lastly, in the scenario 4, all the 3 anomalies are brought to deeper depths altogether. And similarly, the L2 norm joint inversion has recovered much sharper and better separated linear features. And in the sparse norm separate inversions, the inverted values are elevated and the scattering features are more visible and separated. And finally, in the sparse norm joint inversion, the relative positioning of those linear trends are more clearly separated and well-defined. Therefore, it produces the best recoverability with better imaged shapes and volumes of the geologic units. So here is a quick recap on the effect of build depths on the recoverability. So we have found that the deeper units tend to have shorter linear scattering trends, and therefore they are harder to be seen and more difficult to be differentiated. And among the 4 inversion methodologies, the sparse norm joint inversion can help to recover the linear trends even for the deeper units, and therefore produce the best recoverability. So secondly, in order to investigate the effect of the physical property magnitudes to the recoverability, we can compare between scenario 2 and scenario 5, where their anomalies share the same depths, but with different physical property magnitudes. So as displayed in the scatter plot for scenario 5, its north-star unit has a higher susceptibility value. That's why its linear trend is higher above the yellow linear trend for southeast ovoid. While in comparison, in the scenario 2 scatter plot, the red linear trend is below the yellow linear trend for southeast ovoid. So in specifically for scenario 5, the north-star unit has a higher susceptibility value, but it is still the deepest body among the 3 anomalous bodies. Oh, I'm sorry. So similarly, like what happens in scenario 2, in the separate inversions of both L2 norm and the mixed L12 norm, there are only 2 scattering features are recovered, even though the deeper north-star unit has a higher susceptibility here. But with the help of the joint inversion in both norms, this north-star unit is recovered in the scatter plot, and the joint inversion in the sparse norm produces the best recoverability. For the special scenario 6, which also experiments with the effect of the physical property magnitudes, its north-star unit has the same physical property relationships with the southeast ovoid unit, so their linear trends are overlapping with each other in the scatter plot. So in scenario 6, from L2 norm, both separate and joint inversions, there are 2 prominent scattering features are recovered, which as expected, and the differentiated anomalies in the spatial domains are similar, except that the joint inversion has recovered much sharper linear trends. And in the sparse norm separate inversion, the recovered values are greater, and the volumes of the recovered bodies shrinks. And lastly, from the sparse norm joint inversion, the recovered linear trends are further confined, and the recovered anomalies are more detailedly imaged and in both shapes and volumes. So here's a recap on the effect of physical property magnitudes on the recoverability. If we compare between scenario 2 and scenario 5, where they share the same depths but differ in different values. So no matter the deeper north-star unit has a smaller or greater magnitudes in both separate inversions of L2 norm and mixed L12 norm, the deeper north-star unit scatters are mixed up and inseparable. So the recoverability from the separate inversions is poor. While in joint inversion, all the 3 linear trends are recovered. And once again, the sparse norm joint inversion has the best recoverability since their linear trends are better defined and separated. So including scenario 6 with a coincident physical property relationships, we observe that no matter the anomaly has greater or smaller magnitudes, or even with the overlapping correlations, the recoverability is similar. Therefore, the physical property magnitudes do not affect the recoverability as much. So in brief summary of what we have done, in order to investigate the recoverability, we have designed 6 geologic scenarios with anomalies at different depths and assigned with different physical property magnitudes. And in each scenario, we have simulated the gravity and magnetic data and performed 4 different inversions. And for each inversion result, we have also performed the geology differentiation and visualized them in 3D spatial domains. So in conclusion, firstly, the answers to our 2 proposed research questions is that the recovered physical property relationships are not always reliable, and their reliability depends on the depths of the build source body and also the inversion strategies. And secondly, joint inversion has better recoverability than separate inversions. And thirdly, the mixed sparse norm joint inversion has the best recoverability, And lastly, the magnitudes of the recovery values do not matter as much in the geology differentiation because it's a separation and relative positioning of the linear trends that matter the most. So finally, the take-home message from our work is that joint inversion and sparse state constraint, when they are used together into an inversion, they will improve the recoverability of the physical property relationships and therefore facilitates the geology differentiation. So in our next step, we will be working on the Quest project, and there are two motivations in this project. The first motivation is the Quest node terrain has been recognized globally as an important host to several important alkalic porphyry deposits that are rich in gold. However, as shown in this geologic map, approximately half of the survey region is covered by the superficial sediments, especially in the central part, denoted here in the brownish color. Therefore, we would like to use the collected airborne gravity and magnetic data sets and implement the workflow that we have just described to this field area in order to build the mineral prospectivity mapping in this area. The second motivation is that Kim, a former graduate from our group, he has done the L2 norm, both separate and joint inversions to this data set. And based on our synthetic modeling results, we think that it's worthwhile to implement and investigate the sparse norm joint inversion to this data set. And we expect that we could get better results. So to do that, since the Quest region is a huge regional study area, it extends over 400 kilometers in length and over 100 kilometers in width. So in total, it covers an area of more than 48,000 kilometers square. So in order to do the geophysical inversions more efficiently, we have divided the whole region from north to south into 20 smaller tiles. So in the next page, I will show the preliminary results for the first 4 tiles in the north. So from the left column to the right column, it displays the merged model from the L2 norm separate and joint, mixed L12 norm separate and joint inversion results. The first row here shows the inverted density horizontal slices at 2,500 meters deep. And the second row here shows the corresponding magnetic susceptibility models. And the last row shows their corresponding scatter plots. So these preliminary results are coherent with our observations in the synthetic modeling, where the joint inversions has better recoverability than the separate inversions. So in the end, we'd like to thank the SimPEG team for sharing this open source code package used here for the 3D inversions, and the use of PyVista for the 3D visualizations, and also the RCDC at UH for the computational resources. So thank you very much for your attention and time. I'd be happy to have your questions and discussions. Thank you.
Thanks, Xian. I really appreciated seeing, the use of joint inversion for geologic classification and identifying how many different units there are just based on looking at the physical properties without actually bringing that information into the inversion. Very cool. I will open it up for questions. If folks just want to unmute and jump in, feel free to. If we get people talking over each other, we'll do the raise hands thing, but we're a small enough group, so feel free to just unmute and jump on in.
Hey Xinyan, I'll just start with sorry I missed the beginning of the talk. I'll have to rewatch it, but the presentation looks really, really nice. So congrats on the research.
Thank you.
Look forward to see the beginning.
Thibaut's got a question in the chat here. I'll read that out. And Thibaut, you can correct me if I mess this up, but so most of the relationships you talked about were looking at linear relationships. Have you encountered any scenarios where there's nonlinear relationships or tested out nonlinear relationships in the physical properties? So polynomial, log properties, etc. Does that change or have any impacts on the recoverability?
I think this is a very good question. Sorry, but I haven't tried the other relationship or correlations yet. But I think this is a very good question. I will do some experiment about this.
Excellent. Well, we'll look forward to hearing a bit about that. Jiajia, do you want to jump in?
Yeah, just real quick. So in practice, in reality, I'm not aware of this, but maybe you guys do. So do we see any real data example where density stability show like highly nonlinear relationships from the field data? Yeah, I mean, the approach we took here can be easily extended to investigate that, right? But I just don't know if we ever encounter that in practice. And secondly, based on Xinyan's work, I think my gut feeling is that the conclusion here probably will stay true even for those. But anyways, we haven't done that, so something to look into in future.
Yeah.
Thank you for the question, Thibaut.
Yeah.
Well, one case that I can think of is the carbon sequestration project that we're working on. Right, the relationship looks like it's almost like a check mark, so it's not straight up increasing. It has like a phase that increases and then it decreases. But yeah, it's pretty complicated. I have one for you then. I'm interested because the Quest project that you're working on, right? It's not going to be isolated bodies. It's going to be a lot of like domains that are, next to each other, like one big patch next to the other. What's your feeling? What's going to happen if you don't have a zero background? Do you think, do you think it's gonna, because the L1 right now kind of requires the background to be muted, right? If it's not, I wonder how that's gonna work. Would you have any feelings about it? Have you thought about this?
I'm not sure. So can I rephrase your question? So are you talking about like the background or the host rock as zero?
Yeah, exactly. Yeah. Here you're going for relationships of things that are very isolated from each other in a zero background, right? But if the background is not zero, how is that going to work?
Yeah, I think during my inversion, I didn't consider the background too much, because based on the inversion results, when we visualize them in the scatter plots, we can visualize there is a big chunk of the overlapping scatters in the middle part that's kind of with zero density contrast and zero susceptibility values.
All right.
So in my current preliminary geology classification, I'm more focused on the prominent, the correlation trends. And then, I haven't really investigated too much in the central part yet.
Yeah, I think what can help you is that you do have the joint part, right? So you could have some unit that is not at zero, that is just sitting on the offside. So you could technically have a big group not at zero. Yeah, I don't know. It will happen. Something to look forward to.
Yeah.
It's I'm quite interested in your work you've done in the Quest area as well. And something I would point out is that there's actually a very good chemical database which might be able to be used to help differentiate the different regions in the density and susceptibility domains.
So the chemical database for the Quest project?
What I'm saying is that if you look at a map, the geology is not very well differentiated. But you can go in and there's actually been classification work done on the lake sediment chemistry and whole rock chemistry. And you might find that those would be useful to associate with the domains that you've identified in the density and susceptibility.
Okay. Yeah, I think I also found a data set, which is a compilation of all the mineral samples with density and susceptibility values in the whole Quest project. And the previous work done by J. Kim, former graduate from our group, he also used that information to help him to do the geology differentiation based on the geophysical inversion results. Yeah, I would definitely look into that database and use it as a complementary tool for our future geology classification.
Okay, thank you.
Would NRCan have that, Peter? Is that NRCan, or is it going to be just
Science BC has it. You know, the first work that was done by Colin Barnett on the lake sediment chemistry, and then there's work that's also been done by CSIRO using self-organizing maps to produce classifications of different terrains using chemistry. I'm just suggesting it might be a useful overlay that might help you separate some of the features that you're identifying in the domains that you're identifying using susceptibility and density, because it's quite an independent data set, but it is actually pretty well organized.
Yeah, I'll look for that. Thank you. Thank you for your advice and suggestions.
Well, this is quite exciting work. It's good to see.
Thank you.
Hi, Peter. Thank you very much for your suggestion. Yeah, we'll definitely look into that. So in the preliminary work here by Kim, we use the geochemistry to confirm our classification interpretation, but I mean, when we do the classification itself, we didn't actually really consider. We just use that as a after classification verification. But definitely, for Xinyan's work, we are looking to refine the results. So yeah, we will look at the geochemistry data.
Thanks.
Actually got a question for both Xian and Jiajia. So when I'm looking at that cross plot, and I was looking at those kind of interesting hyperbolic features and right there, and like, is that what you're really expecting to see in reality, or like are we expecting more like a kind of like a separate clusters? So what are we in reality, like what's our expectation? Is that kind of like that hyperbolic kind of look like feature, do you think that's actually kind of realistic, or it's actually basically an inversion artifact? Yeah, I'm just kind of curious, what's the expectation here in terms of the cross plots?
Yeah, okay, so like, for example, so in the, front one, yeah, maybe just use this one. So like in our synthetic modeling, because we designed the model with smoothly varying physical property relationships. So in the corresponding true scatter plot, the relationship shows up as a linear trend. So after we do the inversions, we got 4 different scatter plots, and the L2 norm separate kind of like shows like less constrained scattering features. And then when we like doing it in the joint inversion, it's the features are further confined, and then separate inversions also with a lot of scatterings. But in the sparse norm joint inversion, those are like even further confined. And if we compare this one with a true scatter plot, I can pull it up here. So it looks more similar with the true scatter plot, like with very distinct linear trends. But I think this one for the true scatter plot, it's in the like straight linear trends. But here it's kind of like with some curvature degrees. But I think that's because of the inversion, because the model is still like smooth, like due to the smoothness.
Right. Yeah, I kind of understand that part. But what I was kind of asking, because with like Jiajia's previous work on like using fuzzy C-means, or like Thibault's work, for instance, it used kind of like a different philosophy than here. It's like it's thinking about, okay, here's the geological clusters, and then that depending upon the geologic unit, the physical property has somewhat like generates a separate cluster on that 2D cross plots. So to me, that seems a bit more kind of what I would expect in reality. Whereas like here, you're you're kind of putting a linear relationship between mu and rho. See, I was just kind of curious, like, is that kind of, I see that there's a value by doing so, but I was just kind of curious, what's the general expectation on your end about on that?
So are you like talking about like in reality, the geologic model is kind of like the with compact anomaly values?
Yeah, something like that, but not a point, but with some sort of distribution.
Like clusters around it?
Yes, yes.
Yeah,
that's what I
also,
would expect. But maybe I'm wrong, but I'm just kind of curious. So.
Yeah, so we also did this compact anomaly scenario. And so instead of using the clusters, like you mentioned, I used the like single point. So like there is a constant physical properties within these anomaly bodies. And this are our current preliminary results for the 4 different inversions. And we noticed a general recoverability trend. So it's getting better and better from L2 norm separate to the sparse norm joint inversion. The reason I think we built the smooth varying models instead of the compact model is because we think that in reality, in the real world geology, the anomalous body underground might be in a like smooth varying fashion, like instead of like a block model with constant physical properties and then the host rock with another complete different geochemistry. It can be explained by the hydrothermal alteration zone. So like the hot fluid from the mantle intruded into the host rock. And then there is going to be some chemical reactions between the hot fluid and the surrounding host rock. So the reaction will change the mineral compositions of both the host rock and also the hot fluid. And this reaction is going to happen like in a varying or smooth fashion. So if that's the case, then the physical property values will be like in a general like a smooth way instead of like like a sharp change.
Fair enough. Maybe I can jump in here. So, Sogi, that's a good question. So, you're asking what do we expect when it comes to field data, right? That's what you really asked, right? Yep. Honestly, we don't know because this is a huge area, and this is a huge area. The geology is very complex, and if you look at the recovered model from the quest area, the anomalies extend to very deep, like a few kilometers, 5 kilometers, 6 kilometers, or even 10 kilometers. We don't have many physical property measurements that allows to really understand the petrophysics, right? It could be very complicated from one area to the other area. So that's why this work, the motivation is assuming that we have very limited, or assuming that we don't have very representative petrophysics data. We just assume that we have access to airborne geophysical data. Can we use only airborne geophysical data to try to classify the geology units? I think, yeah, in this area, I think that's the case. We don't have much. We have some boreholes, but they are very shallow, right? For the deeper part, we really don't know. So whether it's a good idea to impose strong petrophysical constraint, whether that will improve it out or not, I don't know. Maybe it will improve the shallow part, where the petrophysical data come from. But for the deeper part, we were really not sure. So in terms of what we expect, I think here on this slide, lower right corner, that's kind of what we expect, like a big chunk of a lot of points in the center part, like around 0, 0, and then we expect some spikes sticking out, right? And then the spikes represent a unique relationship between density and stability. And then we have a good reason to believe that, oh, this spike, when plotted in 3D, might correspond to a unique geologic unit. Yes, but this is based on our previous work. So this that's sort of what we expected. Yeah.
I was just that's what I was curious. What were thoughts on your expectation about the distribution? surprisingly, when we're looking at the hydrologic kind of like the logs, it's actually surprisingly Gaussian. So you got a mean, like a generally mean value. Usually variance is pretty large. But I think what we're getting in the geophysical inversion is the reduced variance, because like we're getting the average of those like kind of random distribution. So yeah, but I think in a mining case where we got the weather drop and hydrothermal alteration, probably there's much more variation in the physical property values, I guess. But without those kind of alteration in general, the material seems like, to me, it kind of makes sense to like look like a Gaussian distribution if we don't have much data. But yeah, just a thought. And I also was curious what you guys were thinking.
Yeah, speaking of Gaussian distribution, maybe one thing we can do is that after the inversion is done, using petrophysically unconstrained, right? Just airborne geophysics data, and maybe we will end up with something similar to what we are looking at here in the lower right, and then maybe we can represent this cross plot, everything, all the distributions here, maybe using several Gaussians, right? With different means and covariance. That's exactly what T-bot does. So maybe we can explain what we see here in the sketch plot using, let's say, 10 Gaussians, right? Maybe this 10 each Gaussian corresponding to one unique geologic unit, and each Gaussian has a different mean and standard deviation. Okay. But that's like after inversion is done, and then we're trying to make sense of it. So T-bot, do you have anything? Do you want to weigh in here? You're the leading expert here with the Gaussian mixture of Gaussians.
Sorry, like just let me start camera Miko. Yeah, so I mean, what I like about your approach with the cost gradient, as you said, is like it doesn't take much more input. The only assumption you're making is that there is some sort of relationship between the gravity and magnetic data, which is supported by, it's generated by the same geology. And like when you're going on those large scale, it might be a lot harder to apply the fuzzy mean or the Gaussian mixture petrophysical approach. So that's, and so either, yeah, like, so either you have like different areas that you have to like prior to the inversion define, etc. So, and on SOGIs, yeah, like indeed, like if you have like an isolated target for like something like mining or kimberlite, maybe an approach with a petrophysical inversion will be better, or like give you some more input. But as you say, for hydrogeology, it might not be the case. Well, for Buchmann, what I did with Gaussian mixture worked pretty well, but because in the borehole we were seeing that there was some sort of transition from fresh to saline water. So yeah, it's I mean, I would say like it really comes down of like what's your prior and what you expect from the inversion. If you expect some things that are like very contrasting from a background, maybe your petrophysical approach is very good. If you go on large scale, or if you have something that's, I mean, we're seeing that with the example that Dom mentioned, also with the alteration of ultramafic, where the level of alteration changed the physical properties both in density and magnetic stability, but then there is almost like a continuum of alteration and changing. So like there can be a separated clusters, but these clusters will have like a very different shape, like a V shape as what's shown in the petrophysical measurement. So yeah, geology is complicated. The world is complicated.
Just a comment that you also have the variable thickness of overburden. And so that will kind of soften the spectral response of the geology in the covered areas. And that was one of the reasons that airborne EM was done on this project area, was to give some indication of the thickness or the depth of the cover, which is sitting over the perspective geology. So again, that's going to introduce some effects on things like, you know, the shape of Gaussian distributions. because in some parts of this area, the geology comes to surface, and in other places it does not.
Yeah. Based on the geology paper, I think the superficial sediments in the center part is like in average about 15 meters thick.
Yeah, it's quite variable. It does, but that's true, and that was one of the surprising things, is that the geology or the cover is not as thick as people had originally thought. That the underlying geology comes closer to surface in many places. So it is prospective terrain from a miner's point of view.
Yeah. I'll just double up on Peter with this one. You should definitely consider stripping out that part if you want to help your inversions, right? It will definitely help.
So Dom, you said stripping out the response from the overburden?
Yeah, because it's fairly easy, actually, as Peter said, to at least get a 10 meter roughly estimate of the thickness everywhere, and then just subtract it out from your data and then consider it as air or something. Just at least include it in your inversion, because as Peter said, it will skew your density in a variable way that's going to make it much harder for you to figure out relationships, because you have that overprinting on top, right? Just repeating what Peter said.
So basically you're suggesting incorporating overburden into a model, but assuming that we know roughly the density, stability, and the thickness of the overburden, and then as constant, right?
Either that, or you just forward model the overburden. If you have an estimate of it, and you just subtract it out from your data set beforehand. I don't think it's susceptible, but it's going to be low density.
Okay.
If the goal is extended, now let's say you got lots of well data or other types of data. So now we're sort of doing an unconstrained inversion. But Xinyan, are you planning to integrate other types of data into your inverse framework? And so what I can see, just with the geophysical data, what we can tell is quite limited, I guess, because like as we discussed, we don't actually know the physical relationship between each parameters. So likely in the Quest region, you may have lots of actually ground truth data, I guess. Are you, oh, maybe not.
I think there are several well-known deposits like Mount Milligan. So we probably, we will look for some known mineral deposits and maybe mineral sample data to help us to constrain our inversion results and use it as a complementary information into our geology differentiation. Yeah, I'll look for it.
And there's a ZTAM survey, right? But we're not there yet in terms of inversion. It would be nice.
So our end goal here is to map out the prospective bodies in the center part, where we have this thick overburden. Sorry, my daughter just came back home from school. We want to map out the prospective bodies, like future exploration target in the center part. So the basic approach we took is that because we know the known deposits in the north and southern part, right? And then we can associate that with their geophysical signatures or response, or maybe physical. Yeah. So for example, maybe some of the, based on Kim et al.'s preliminary work, we found that some of these linear trends in the first quadrant, Xinyan, can you point to the first quadrant? Yeah, there. Some of the linear trend actually corresponding to the known deposits in the north and south part of the Quest area. So if we look at their 3D visualization also in the central part, then some of them might also, because they have the same density and susceptibility, right? Same geophysical signatures. So basically we're doing like a pattern recognition, and we recognize, we use the known deposits, and also we have the inverted density susceptibility everywhere, right? We're just trying to identify those densities and susceptibility values that correspond to the known deposits, and then we extrapolate this pattern and apply that into a central part, and that helps us determine the prospective area. So that our end result will be a map showing what are the potential mineral targets in the center. That's actually, if you go to this this preprint here, came out of 2021. That's our last image showing a few targets in the center that we identify as prospective mineral targets. Xiaolong, go ahead. You have something to say, right?
Yeah, just I want to say, I remember the EM data is also available in the areas. So yeah, maybe something we can do, join to the EM using the SimPEG one day in the future. Just a comment.
That will be a second PhD.
Yeah, it's a big project.
Excellent. Well, we are coming up on the hour. Are there any final questions? No, if not, a big thanks to Xinyan and Jiajia for this presentation. Really interesting work. Very excited to see your papers coming out soon, hopefully on this. So thanks so much for taking time to share it with us and putting all of this work together to present to the group. So we will get your talk up online shortly after this, so you can share the links with anyone. And next month we will have Craig Miller. And as I mentioned, we'll be looking for speakers after that. So if you or anyone else that you would like to hear from, if you'd like to reach out and just let us know who you'd like to hear from next, we can tap folks on the shoulder for coming up upcoming SimPEG seminars. So thanks so much, everyone.
Thank you for having me.
Thank you, Lindsay. Thank you, everyone.
Thank you.